In this lesson, we present to you the Pythagorean theorem. This theorem is one of the fundamental theorems in geometry that links this branch of mathematics with algebra. We will be showing you two proofs of the Pythagorean theorem. We hope you enjoy!
The Pythagorean theorem states that in a right triangle such as this one, the sum of the squares of the two shorter sides, in this case A and B, which are known as the legs, will equal to the square of the longest side, known as the hypotenuse, in this case C. The algebraic formula for what I just explained is written right here. A squared plus B squared equals C squared. We're going to show you the proof right now.
Now I will present to you the Pythagorean theorem proof. For now, we have two ways to prove it, even though there are more than 100 ways to actually prove the Pythagorean theorem. We will present two ways. So, to prove it, we first have to know our given. Our given is a right triangle with legs A and B and a hypotenuse of C. What we need to prove, though, is that the side length A squared plus the side length B squared, when they are summed together, you can get the hypotenuse squared. That is what we are trying to prove. The first thing we can do is we can create a large square with side lengths A plus B together. That way we have a large B squared and a smaller A squared with four right triangles that we have been given. The area of this larger square is A plus B squared because it's a square, and that's why that is what is shown there. After looking at the first square, we can see that we can create another identical square that also has an area of A plus B squared. Inside the square, we can create a C squared square. That's kind of repetitive. Okay, but with the sides of the square being A plus B, ABC triangles that were the given. This C squared square we know it's a C squared square because these right angles are created because the fact that these angles plus this angle are going to be supplementary. Then we also know that the hypotenuses of these right triangles work together to make this square. Now we know that this figure has an area of A plus B squared. That we know because it's A plus B side length and it's a square. But we also can see that this square, the area can be shown here as AB over 2, which is the area of one right triangle. You multiply it by 4 times to create the 4 triangles, and then you also add the C squared in the center. Now that we know that this square has 2 different ways to express its area, we can now create an equation with A plus B squared on this one side, and also our other statement, 4 times AB over 2 plus C squared on the other side. Let's evaluate it. And voila! Now we have our Pythagorean theorem and proved through an algebraic and geometric method. This is our first method in proving the Pythagorean theorem. This method was devised by Pythagoras himself. Now I am going to show you the second method to prove the Pythagorean theorem. This method was devised by an Indian mathematician, Bhaskara. What Bhaskara first did was that he blew up the triangle so that he could see it. Duh. And then what he did was that he dropped an altitude to the hypotenuse. Sorry, I can't draw straight lines. Anyways, after he drew the altitude, he wanted to prove that this triangle was similar to the larger triangle, which we can do right now. If you see here, I've labeled the side lengths now, so that it could be clear when we write the proof. Now, we want to prove that the triangle ABC, which is a right triangle, as has been given, we want to prove that it is similar to the other smaller right triangle within it, BEC. To do that, we must look at how we can prove it. By looking at it, we can see that from the larger right triangle, angle B is complementary to angle A because of the fact that the angles in a triangle must sum up to 180, and one of those angles is already 90 degrees. Given that, we can see here that B has its value, angle B has its own value, and then we have another right angle here, which means that this angle right here, angle BCE, must be congruent to the angle A because of the fact that angle B is complementary to angle A, and it is also complementary to BCE. Now, after that, we must find another angle to use AA similarity to prove that these two right triangles are similar. What we can do now, we can use AA similarity to prove that these two right triangles are similar. This is because we know that angle B is also congruent to itself by the reflexive property. Now, we have two sets of angles that are congruent, and so by AA similarity, the triangle BEC is similar to the triangle ABC. Now, using the same idea, we want to prove that triangle CEA is also similar to the larger triangle. As like before, we think that AA similarity would be the best way to approach this problem. Once again, we know that angle B and angle A are complementary. And from this diagram, we can see there's already a right angle in triangle AEC, which means that angle ACE must be complementary to angle A as well. Now, we know that angle A is complementary to angle B. And we also know that it is complementary to angle ACE. From here, we can have AA similarity again, because since A is complementary to both of them, these two must be congruent. Thus, angle B is congruent to angle ACE, and angle A is congruent to itself by the reflexive property. From this, we can use AA similarity again to show that triangle ACE is similar to triangle ABC. After proving that the triangles were similar, as seen here, BC is similar to BCA and ACE is similar to ABC, we now can derive some ratios that come from the similarities. From the similarity triangle BEC similar to triangle BCA, we can see that the ratio of x to A is congruent to the ratio of A to C. That is because it is the shorter leg to the hypotenuse and the shorter leg to the hypotenuse. And we can show that as this ratio, x over A is equal to A over C. We don't really like denominators, so let's multiply both sides by AC to make it look prettier. Sorry, I don't have space to put AC on both sides, so let's just do it this way. And this is what we get. Now, let's do the other triangle. Triangle ACE is similar to triangle ABC. And from that, we can also find some other ratios. The ratios we can see here is the same as the previous one. We can show that Y to B is the same as B to C. This is because it is the longer leg of the right triangle to the hypotenuse, and the longer leg of the other right triangle to its hypotenuse. We can express that as Y over B is equal to B over C. Now, again, we don't like denominators in this case, so let's multiply both sides by BC. Once again, I don't have space, so I'm going to have to express it in this way. This is probably not the right way to express it, but we're going to have to do that in this case. From this, what we can get is the following. YC is equal to B squared. Those are the two important ratios in this problem. Now we have two equations. From this, we can see that, oh look, there's C's here and A squared and B squared. Well, we want to make A squared plus B squared equals C squared. So why don't we sum the two equations together and see what we get? that really doesn't look like a squared plus b squared equals c squared. Why do we have an xc plus yc? That doesn't equal c squared, does it? Well, to find out, let's factor out that c. Alright, we factored out the c. Now, we have x plus y inside of parentheses. But what's x plus y? What am I missing? Well, it turns out that x plus y is actually c, because these two were variables that we set up to express the two shorter side lengths that sum together to make c. So that means we can replace x plus y with c. And what does that give us? That gives us a squared plus b squared equals c squared. And that is the second method to prove the Pythagorean theorem. This is Basquiat's first proof, and he also made a second proof, which is much more complicated, and we don't really want to touch up on that in our video. We also want to say that the 20th President of the United States of America, President Garfield, also made a proof of the Pythagorean theorem, which was really interesting. He made it 5 years before he became president. And so, we want you to go on the internet and search up President Garfield's proof of the Pythagorean theorem. Thank you.